Hello, everybody, and welcome to the May 2026 Inventors Gathering. I'm very pleased today to have Lawrence Kincheloe and the Biochar Toilet team presenting. Before I introduce Lawrence fully, let me mention that Public Invention, just 3 weeks from now in Austin, Texas, on Saturday, June 13th, is having the Public Invention Con, which stands for both convention and conference, in Austin, Texas, in the downtown library, in a really beautiful space that we've rented. We have a great keynote speaker coming in from Scotland. We have quite a few people registered and a really great lineup of speakers and demos. And this team that's presenting today is going to be demoing some parts of their biochar work, which should be really fun to see that happen. So if you happen to be in Austin, Texas, or can travel, I'd like you to consider doing that. We have an Eventbrite, which you can find. Megan will post it here in the chat for people. And it's really going to be a very good time, I think. Okay, let me now attempt to introduce this project. This is a really good project in the sense of the impact that it could have on people around the world. It's a very important project. You know, it involves sanitation, and as one expert on sanitation once told me, you know, a bar of soap has saved more lives than all the doctors in the world, in the sense that although sanitation is not glamorous, it prevents the spread of disease, which kills more people than all the bombs and rockets and bullets in the world. I don't know if we should be happy about that or sad, but nonetheless, that's the case. So this team, I sort of started it, but it's now being led by Lawrence Kincheloe, who's volunteered for about 5 years for Public Invention, has worked on the NASA project and a number of other projects. He's a man of very broad intellectual taste. He's developed board games. He's an artist who's made interesting installations that light up and do that. And he knows a great deal about a large number of topics centered around electrical engineering, but he also knows some things about chemical engineering, which I'm personally rather weak on. And so in conjunction with Public Invention, as we do, we have formed a team consisting of Peter Shryock and Hardik Pila, who have been helping Lawrence with this, and he's going to now introduce. So let me hand it over to you, Lawrence. Take it away. Thank you.
Thank you. So Peter's been helping with the mechanical engineering aspects of it. He's been doing the helping with getting the physical drilling and manufacturing, and then also some of the CNC work. Hardik's actually put together the phase 1 prototype that we'll talk about, and he's done a lot of excellent work on the electrical engineering work, putting together the PCB design for the control systems. And we're looking forward to getting that integrated into the phase 2 that we're in the process of putting together. Let me share my screen. Okay, so this is the Biochar Toilet, open source sanitation. You can find us on our GitHub page at Public Invention /Biochar Toilet -toilets, or you can find us at the main Public Invention website. So the main thing we're trying to get across is that the way biochar toilets kind of fit into the infrastructure gap inside of the sanitation system. Primarily, there's a lack of sanitation across the world. Usually, there's at least some level of sanitation, but there's without like access to a modern septic and sewage system. There's or if you're in a place where like water has become more scarce due to climate change, sanitation is usually the first thing that takes a hit. Also, the energy required to maintain a sanitation system If there's any disruption in the energy infrastructure, that can be a major impact. So what we're looking at building is a type of toilet that both is more efficient than some of the other options out there, and also provides a carbon sink, as well as a couple of other benefits that we'll get into. Just to kind of throw out like the type of traditional sewage systems we're dealing with that people are kind of familiar with. There's the flushable toilet is the main one that everybody's mostly familiar with. You see them all across the world, and then in different parts of the world, there's different levels of how complete of a system they are. Sometimes they're rural and they're based on like a septic system where they have to be pumped out on a regular basis, or they're in other parts of the world where they don't have a good sewage where you always have backups, or you can't flush what we normally flush down our toilets, or they get clogged regularly. And the main problem is that and this is a problem with all traditional sewage, is that you can't really flush greases down. You can't really flush there's a lot of things that you shouldn't flush down toilets. They cost a lot to maintain. They use a lot of water. We're also going to talk a little bit about composting toilets. Composting toilets are interesting because they're normally considered to be the kind of like the gold standard for renewable low-cost toilets. They do produce, and compost toilets basically use aerobatic bacteria to basically break down fecal matter into human manure, or basically it's just low grade fertilizer. It does have problems because it doesn't get hot enough normally to kill all pathogens unless you have a specialized containment system that's designed to basically reach passivization or temperatures like 165 degrees for several hours. And they also, unfortunately, require a lot of manual intervention. So these are things like basically like taking dry material, putting it over the fecal matter, and then having to take the whole bucket and then take it to the composting area. If you're familiar, if you haven't heard about them before, there's also something called the incineration toilets. These are usually used in boathouses, or they're on lake houses, or places where they can't put sewage directly into the ground. And they're normally designed to use high temperature to fully incinerate in an oxygen environment fecal matter. They have they create a lot of CO2, and they use a lot of energy because they are a non-contact conductive heating source, and they get hot for a long time, and they have a long cycle time. Also, the output of the ash is not as it's not a CO2 sink, and it also doesn't have as much nutrient value as our system. And finally, what we're talking about today is the Biochar Toilet. Our current innovation uses a pulsed heating system using induction heating. And we have a process for sterilizing not only the chamber on a repeated basis to keep it pathogens down, but also to handle the water moisture content, and also the noxious gases that can come off of the system. The byproducts also are carbon sink, because we don't the biochar toilets in particular this process is a pyrolysis process, which means that there's oxygen is not used in the carbonization of the material. So what happens is basically everything that's not carbon gets kind of gasified out, or all the oxygen molecules, all the water molecules, anything that's vaporous. So just to deep dive back into sewage, main issue, yeah. So the main issue is the, like, not only is it just the, it's hard to kind of explain because I mean it's not always obvious, but it's not just um, the energy intensity of the application. It's also the infrastructure that has to be required to build up the infrastructure, the system. You need miles and miles of sewage line to go back to the sewage water treatment plant. You also have to have clean, fresh, potable water used for sewage. And then when anything, if anything breaks, or if your city keeps on expanding, or if your city contracts, there's not an easy way to basically like maintain these lines, especially like when lines have like a 70-year lifespan. We've got cities that are over like 100 years old in America, and like in various cases, water quality and sewage lines are the most expensive things to fix when they all kind of hit at once. And so just to kind of dig into a little bit deeper, like to kind of like bring it home, like water is the biggest limitation we have coming up in the next 21st century. We're already seeing that in certain towns where cost of water becomes an issue. There's no risk of runoff in places where they don't have good sewage separation. Our system is designed to basically only require electric power, which means that it doesn't require a large amount of utility grade infrastructure to keep it going. And the byproducts are all solid sterilized biochar. And the biochar itself has agricultural value as well as other applications. Composting toilets, they do have a lot of benefits. They're eco-friendly, they're low resources, they're off-grid capable, but again, like they require a lot of maintenance. Most of us never grew up with having to have an outhouse, but a composting toilet requires you to take your night waste and then dump it into a composting facility. There's no real getting away around it. It can't be composted inside of your home. Odor is always going to be an issue, and then it just takes a long time for it to break down. From a regulatory standpoint, also, it's not really easy to deal with from a regulatory standpoint because it's not managed in a way that can be regulated easily, like a sewage septic system or anything else where it's separated into a holding cell, and then a company manages the waste retrieval.
Yeah, perhaps I could jump in here and mention that no matter what you do, compost toilets attract flies, and it's not harmful. It's just annoying.
Mm-hmm. Yeah, and so just to take a little bit of a deep dive, like in a composting toilet, like we don't have there's not a way to sterilize the compost. There's no way intrinsic to the composting toilet to sterilize the composting toilet. The composting toilet also doesn't if the composting toilet does not have gets contaminated with waste material that either is hard for it to break down, or it doesn't break down, then it won't break down because it's basically reliant upon a bacterial culture to basically break down the material. The composting toilets require like a input in the terms of like sawdust, dry soil, peat, or some other kind of material to kind of like soak up moisture, and then also allow it to compost. And then also the output is also not as it's good. It has a good use case for fertilizer, but it doesn't have like a great like use case. It's not as good of a use. It's not as good. It's not. I mean, it's a good use case, but it's not like a home run of a use case for human manure in particular. Incineration toilets kind of have a similar kind of setup. The incineration toilets require you to use a urine diverter. They're not really designed to handle like because all the material inside them has to be boiled off. They recommend that you don't basically urinate inside the toilets. They do have sterilized. They are completely sterilized, which is nice, and they do create like a low compact volume of waste that can be easily distributed or gotten rid of. But the main problems are that they're very energy intensive. You have to basically bring it up to incineration temperatures and maintain that temperature for a long period of time to be able to reach the both the sterilization and the volume reduction. And because they're contact based, they require a lot of continuous AC power or energy, and that can be kind of costly in most environments. So again, like energy is a big issue. The ash itself is not really useful as a soil additive. It doesn't really do anything for the carbon cycle, and it's and there's not really it doesn't really our current design that we're moving to phase 2 is more efficient than an incineration toilet, because of some of the features we'll get into. And this kind of covers the same thing I just said. See if you have any questions about incineration toilets, because they're probably the closest to a biochar toilet. And if you have any questions about like why not burn it, this is probably the best time to ask it. Okay, well, moving on. So when we started this project, we kind of had a couple of high-level goals: sanitation, carbon sequestration, open source, and then a fairly very aggressive total cost of ownership. So that basically means that like the energy input and the consumables in the device have to be relatively reusable on a regular basis, while also being automatic and also self-sterilizing and fairly like one button push to operate. Our initial proof of concept, which Hardik primarily led, was that we were looking for a way of heating up the material in a non-contact fashion, using a pressure cooker as a baseline pressure vessel, because it allowed us to produce flash decompression, which allowed us to create a sterilization event, as we basically created a rapid pressure change. It also allowed us to create a high pressure steam environment, which allows us to basically act as an autoclave inside of the pressure vessel. We used a fairly innovative dryness detection monitor. And so what happens is that we kind of burp the pressure vessel. So we heat it up and we use a pressure transducer to measure we use a pressure transducer to kind of measure the pressure increase. And when we reach a point where the pressure stays constant and the temperature continues to increase and rise, we know that we've got a divergence in the pressure and the temperature, and we know at that point that we've reached a level of dryness, or as dry as we can basically get it. And so that's the algorithm we're currently using for detecting dryness in the system. So we're not using a moisture sensor. We're not using a complex temperature monitoring system. We're basically just measuring the pressure rise, and then when the temperature rises and does not continues to rise, and the pressure kind of stays static. We do have a video of the system that Hardik put together, and let me see if I can get this to play. So what we're seeing here is this is the board that Hardik put together. This involves an ESP32, a solenoid driving circuit, and temperature monitor, as well as a pressure transducer monitor. This system uses a hot plate for heating the pressure cooker. Right here, you can see the on the left-hand side a wire coming up into the pot. That is the thermocouple going into the sample. There's a manual pressure transducer to visualize the pressure level of the system, as well as a digital one, electrical transceiver, to be able to measure and record the pressure inside the pot. And those two bits of information are what we use to calculate dryness, as well as to know when we've dewatered the system.
The pressure transducer is right near the wall.
You can see here we've got the valve parameters. The heater is currently on, and it's not. We say it's not dry. We have the temperature and the duty cycle. So so that's phase one. So phase one basically produced a I don't have a good picture of it, but it basically produced a nice charred bread sample, and it also created a good test base for like what features we basically needed to hit next. So for example, I think the original one we used like a 1/2-inch diameter pipe. We're going to move that up to a 1-inch diameter pipe to allow us to have a larger pressure drop in the environment. And then we're also going to look. We also found that it takes quite a long time to get to temperature, as because the original our phase one system used a conductive system, so it was heating from the bottom. And so as the material began to pyrolyze, it became a insulative material, and so it would take a long time for it to actually heat up. So our next system, our phase two, we're looking at transitioning to induction. Induction has some really interesting properties. So induction basically is a way for us to heat up magnetic particles inside our fecal sample. And so what we did is we decided that we basically kind of took a note from kitty litter boxes, which use a bentonite or calcaline style clay. And we added into that a magnetite material, which is a magnetic susceptor. And it allowed us to basically heat up the magnetite and directly heat the material that is in contact with the kitty litter. So induction also has a couple of interesting properties. It's a contactless energy transfer, which means that you can fully insulate the vessel, because you don't have to transfer heat to it through conduction or convection. You can directly heat everything that's making physical contact with the sample. It also like rapidly, because we're doing direct heating of the material in contact with the fecal sample. We also have a much better thermal transfer process for rapid heating and dewatering. It also is convenient because we can fully seal the vessel, the pressure chamber. In the previous project, we were looking at like how we could basically increase the rate of heating, and the only option we could really come up with was to insert like thermal probes directly into the sample, which would then again have the same problem where like you want to have your heating source directly in your fecal sample to increase your rate of thermal transfer. And the nice thing about the induction system is that you can basically isolate that so that the fecal sample stays inside of a container that can be easily autoclaved and easily cleaned and then removed. Yeah, we talked a little bit about this, but so the other neat thing about our system is that we use the bentonite clay has a couple of other interesting properties. So the clay is actually an ultra high surface area, and it also acts as a desiccant. And so what happens is that the clay material actually wicks water away from the fecal sample or from the urine sample, and it evenly distributes it across the entire clay body. And because the clay body is incorporated with magnetite, you basically get like millions of different nucleation sites for water to boil off. And so the dewatering phase can rapidly boil off like a entire content of water in like minutes. So we can basically boil the whole thing dry very rapidly. The other innovation that we came up with was that that the magnetite itself has a fixed Curie temperature. Because it's a ceramic material, it's also very durable, and it's also very cheap, and it's also non-toxic. So the neat thing about this is that like if the system breaks down or we don't have to deal with having a complex temperature management system, because the material inside the magnetite itself can't get hotter than like I think the maximum temperature is like 500 degrees F, and like it won't get hotter than that. It basically demagnetizes and becomes non-reactive to the electromagnetic field when it gets too hot. And so we can build a enclosure that can handle those temperatures, and it'll basically be self-correcting in terms of temperature. The other neat thing about this is that the system that we're currently using, this is really convenient for the Austin trip as well, because we had problems with getting the power configured correctly. But our system currently uses like a 48 volt power supply, a DC power supply. I think we're using like 50 to 80 amps. But because we've got such a short time of we can actually use a 48 volt battery pack to run the system. And this has a couple of benefits. One, because it's DC powered, we can actually run the whole thing off a battery and then also a hybrid inverter. So this would actually allow us to design the system to either take in 48 volts directly from a battery pack or an inverter, or we can use a power supply and run that directly off of wall mains. And that allows us to basically create like an off-grid, highly efficient solar-powered toilet that uses a solar power to charge a battery that then can run whenever you want to use it. And because our cycle times are so low, we can build a system that can handle several peak power surges that when you need to use the restroom, it's ready for use. And this is something that's important about public invention is public invention tries to endeavor to use open source wherever possible. So in our design, we used open hardware as much as possible. We used KiCad for our schematic capture. We're using ESP32, which has open hardware or open source firmware libraries for its application. Our firmware development is using Platform IO. And then all of our hardware fabrication and enclosure and mounting brackets are done using FreeCAD to make it as replicatable as possible, and also easy for people to participate in the project at any level that they see fit. So talking a little bit more about the value of the biochar that this device creates. Biochar actually has a couple of interesting properties. Not only is it so biochar itself is you can think of it as like pyrolyzed carbon. So it's essentially carbon that has had all the hydrogen, or some of the hydrogen and most of the oxygen stripped off from it. It's usually a semi-crystalline material, and it only has a very high surface area. It actually has a couple of interesting properties where when it's added to soil, it actually acts as a moisture sink, a nutrient sponge, and more importantly, in this particular case, it also acts as a carbon sink. because it becomes non-reactive, and it's because it's self-contained, it basically doesn't degrade further, and it basically stays in the soil as a high volume absorbent material. But it's also renewable as opposed to some of the other materials that normally people would use for like moist, to add more volume and soil retention to your soil. And it's not like a peat, or it's not like a mineral based high surface area material. So thank you for coming. And does anybody have any questions?